Welcome. So a few people in for the long haul that joined us earlier today. So those of you that have just joined us, thank you for coming. I'm going to hand over to Hartwig very shortly. We are streaming the sessions. We've got a few people watching online as well, just live there. So what we're going to do, we've got a session here with Hartwig's going to go through some of the experience that they've had overseas, because I didn't mention it from earlier, but one of the big points of this is that we're not as special as we like to think we are in New Zealand. I often hear that, oh, New Zealand's special, and we are special. But we're not that special in terms of our building, our climate. As Thomas points out, physics works here just as it does in the Northern Hemisphere. And the point is that we are a fair way behind a lot of countries, and the process to get from where they were to where they are has been anywhere from 20 to 30 or longer. We don't necessarily have to go through that painful 20 years of trial and error and reinventing the wheel and using number 8 wire innovation to fix things. We can actually copy or learn from what has been done elsewhere and apply it to some of the unique features that we have in our marketplace. That's what we're here to discuss about tonight. For those that have just joined us, if you do need to go use the bathrooms, they're in the bottom of the other building. Just wander out through there, up the corridor. If you do need to grab yourself another drink or anything during the session, help yourself. We will be swapping and also hearing briefly from Jesse for more of the local perspective, and then at the end we'll get in amongst it with some practical stuff outside as well as having some socialising and networking. There was something else I was going to say, but I can't remember what it was, so I will hand over to Hartwig.
Yeah, thank you, Matthew. Well, welcome to those who have just joined us. My name is Hartwig Künzel. I come from the Fraunhofer Institute for Building Physics in Germany. And we have a large field test site that we see here that was set up in the early 50s. And there we've been through a lot of things. We had the possibility to investigate, I would say, almost every detail of the building shell. And we also saw what is durable and what is not. This is quite important. And another important feature is if you have such a field test site, usually you have to wait quite a while until you see damage, because it takes a while. It takes a while until you get moisture damage, takes a while until you see that there's a problem, maybe with leaky windows or something like that. And if you don't want to wait, then you can apply the same thing in the laboratory. But if you do exactly the same thing as in the field test, then it would take the same time. So what you try to do is you look at the most severe conditions and repeat them all over. Severe conditions that happen maybe 2 or 3 times a year or something like that, where you assume that there might be a problem. You replicate this in the laboratory and do this, let's say, every day. And then you figure out how long that would last in reality. Let's say if your window connection or whatever fails after 3 weeks, that would be maybe 30 years in reality, something like that. And in order to get to this point, it's quite important that you have both capabilities, doing experiments in the field as well as doing them in the laboratory. If you don't have that, then you can't really compare what you're doing. You don't know what you're doing. And it's also helpful if you can do numerical simulations that can support what you're doing in order to find out what is actually happening. In a numerical simulation, if you find moisture damage and you don't know where it comes from, if you have around the window moisture, it could be condensation from the interior environment. It could also be liquid water that penetrated the exterior seal. So sometimes it's difficult to tell. Is it what was the main mechanism that led to damage? And if you have a numerical model, you can try to do parametric studies, look at what moisture content would you get if you had, let's say, convection from the interior air, or just vapor diffusion, or whether you had wind-driven rain leakage, something like that. An indication is already when you look at the orientation where the problem occurred. If that's the orientation where most of the wind-driven rain comes from, there's a likelihood that it's the rain that caused the problem. But that's not always the case. Sometimes you can have a problem from the interior side that was caused by pressure differences. So if your wind comes more from the east, you tend to have a lower pressure at the western side, so you could also get air going through in this direction and have more problems with condensation. So therefore, it's tricky, and it's good if you have several possibilities to test things. And later on, I will show you some tests that we've done here. It was not really an intended test. It was just we looked at the exterior insulation here in the windows in order to see what happened. But that's the story later on. Yeah, these are our possibilities to test windows and their junctions, connections in a climate simulator where we have a hot, or let's say warm, humid climate on one side and a cold climate on the other side. Yeah? And then we apply a lot of sensors in order to see what is actually happening, what temperatures do we get on the frame, in the window, at the window joints and connections. I think this is quite important. And if you get some air flowing through it, then this will have an effect on the temperature that you're measuring. So you can already find out there might be something wrong. Then, of course, you have to apply water. This could be condensation water. This is the case here, but you could also have wind-driven rainwater. We will go to that. And you see what effect it has. What is going to happen with the water? Does it drain where you want it to drain, or doesn't it? So these are all the experiments that need to be done in order to find out whether a window works and whether the window wall connection works. Here we have for larger facade glazings the possibility to apply pressure and wind at the same time in order to see how good the seals are and how durable they are. And usually you go up to pressure differences that you won't find in your building. Yeah, maybe if you have a hurricane or something like that, but otherwise not. Because you want to be sure that this works. If it works under a very high pressure differential, then the likelihood is large that it will also work under normal conditions. Here, another picture of the investigations that we are doing. And it's not only us who are doing that. In Germany, there are several accredited laboratories that do window testing, window wall interface testing, and so on. One is also in Rosenheim. And I think some of the test results that we will see afterwards from Jesse have been done in Rosenheim. And we are also working together with them. This is again one of these hot box, cold box tests. Another test that's really quite important is windows are subjected to large differences in temperature. When you have radiation, when you have an insulated window, it's even worse. Let's say you have the exterior panes, see completely different climate from the interior pane. Double glazing and triple glazing, it's even worse. That means you have also different dilatations, expansion and contraction of the different window panes. So the whole window is working. No? And chances are that the whole thing becomes leaky are greater. When you just have one single pane, sorry, a single glazed window, the problems are not that big. No? So that's something we have to test. And if you have a large glazing system, of course, it's even worse. And if you have shading within your window cavity, then you have also differences in temperature over the height of that glazing unit. So this is very important to investigate all that, and also to investigate whether there is some airflow through some of the holes there. Sometimes you need this, you need some holes so that water can be drained away, and the question is, do they have any connection to the interior side? Because that would be not a good idea. No? It should only be for the water drainage and not for the air passage. U value of windows is quite important. Therefore, we routinely do the hot box, cold box tests, because what you usually do is you just measure your glazing unit, then you have your frame. If you put all of that together, you have thermal bridges that you have to take care of. If you want to have a high performance window, you need insulation in the frame, and the whole thing has to work well together. It's too close, okay. Sorry. Check this. Yeah. So, and I guess you probably know how a guarded hot box works, that you have an insulated box here, you have the same temperature all around in the vicinity, and all the energy that you supply here will go through your window to the other side, and you can measure exactly how much energy you supply, and so you know exactly what the U value of your window is. Now the question is, if you have a window, from the thermal point of view, what would be the ideal location? And I've heard that you put your windows more to the outside of a wall. This has also been figured out in Germany, so we tried several different possibilities. This is a homogeneous wall. These are masonry walls where you have the perforations. That's also to increase the R value. Sometimes you even have here some insulation in there. Now, there's a question, does it matter whether you install your window in the middle, more to the interior side or to the exterior side? And that's something that we have studied. And here you see, for instance, these are the temperature distributions in the wall, in the frame and the window, and the heat fluxes here. You see it looks better when it's in the middle, but we will go to that more closely. Here, the window is at the exterior side, and you see that you have it warmer here, but at the corner of the window, it is getting colder. And this is something you can also see here. If you look at the temperatures, these are different kinds of window wall variants. Yeah? More homogeneous walls, less homogeneous walls. But it's the same thing all over. This is the surface temperature. This is when your window is completely at the exterior side of the wall. And this would be the case if your window were at the interior side. Yeah? And you see that if you put it to the exterior side, then you have colder temperatures there. So the likelihood of condensation around the window is greater here than it would be here in the middle. In the middle, you see you can play around a little bit. There's not that much change. Yeah? So that's the situation with the temperature. Let's now look to the situation of your U value. So you can measure the U value of a window. You can measure the U value of your wall. Or you can also calculate it. Now, there is an additional U value or additional heat losses because you have this connection between window and wall. Yeah? So you're losing additional heat due to that connection. Now, the question is how much and how do you represent this? And internationally, we take something, it's a psi value, that's a linear U value. So you calculate the length of that connection, multiply it with that psi value, and then you know how much energy will go through it. Yeah? That also means the lower the psi value, the better your window, the better your window wall installation. Yeah? The less energy you're losing. And you see here again, this is the psi value, and this is exterior, this would be in the middle, and this is the interior side. And I think you can clearly see that it's much superior from a thermal point of view to have the window in the middle versus having it on the outside or the inside location. If you have to put it on the outside, then you might need some additional insulation around or something like that in order to avoid that problem. You see there is a factor of more than 2 in between. And if you have many windows, this becomes quite apparent. So when we look to our European regulations, this is something you have to show. This is something you have to calculate. So if you have a bad wall-window connection, then you need more insulation somewhere else, which is maybe not a very good idea, or a more expensive window, something like that. So it's also the choice where you put your window. I think Jesse will show you that a little bit more for the constructions that are more in use in New Zealand, whether it's the same thing or not. And I guess it is. Well, let's now talk about the problems with leaky windows. More than 40 or 50 years ago, we started to insulate our buildings on the outside. So in Germany, we build new buildings, but we have a lot of older buildings that have to be retrofitted thermally. And the usual way nowadays is that you apply an exterior insulation system. So you put polystyrene boards or mineral fiber boards on the exterior wall, you glue it on it, then you put render on it, and or stucco, as they say in the United States, and usually that works quite well. We have a lot of experience. Of course, you have details around the windows that you have to look at, but when we did inspections of buildings that were equipped with such an external insulation system, we saw that they all work pretty well. So the question was always, is that external insulation as durable as a normal render on a masonry wall, or is it worse? And everybody thought, well, if you have this foam insulation that can't be very durable, we cannot imagine that it's good, and we could prove, we investigated that over 40 years, I could say almost, that it's really working. So we were sure this is a damage-tolerant construction where you don't see problems usually if you do it right. And apparently most people did it right. And when I came around the turn of the century to the United States, they told me, well, that stuff you brought in here from Germany on Canada just doesn't work. Our buildings are rotting away. And this external insulation system that they call Eaves in the United States is to blame. So I was wondering, I can't understand. So there must be something that they're doing wrong. Probably no quality control, crappy workmanship, or whatever you think about. And then later on, then we tried together with the Americans to find a solution. Well, they said, well, we tried everything. It's almost impossible to seal it in a way that the window doesn't leak. We might need an additional drainage plate or something like that. Or are there other solutions? So we tried to help to find solutions and looked at it. So that's the normal construction. While this is mostly concrete or masonry in Europe, in the United States, it's usually 2x4. And of course, you cannot put that much insulation inside, so it makes sense to add a little bit. I think it's usually 5 inches or something like that of insulation that put on top of that. And it has two advantages. First of all, you have no thermal bridges anymore. That's one very good thing. The other thing is it's very easy to plaster over it, to render over it. To apply a render to polystyrene boards is very straightforward, and you need only very thin coating, which is a good thing. And therefore, it's also called exterior insulation finish system. So it's an easy finish system, I would call it. Now, what happens? You get some rainwater in here. What I've also learned in the United States that we don't have at all is a drainage plane behind the render. You have usually building paper, there's a drainage plane. This is unheard of in Europe. We apply the render directly on our masonry. It's all face seal. Nobody ever thinks about a drainage plane. And therefore, companies that came from Germany, like Stoll, did not install any drainage plane. They just did it as they always did it. Applied it directly here on the OSB. They glued that insulation layer and then they're stucco. Now, if you assume that some of the water gets in here, the question is what will happen and how much can get in there. So after a while, we agreed that it's probably very difficult to prevent all water going through. And we saw, well, if it's only 1% of the rainwater that will hit that exterior surface, then maybe it's not a problem. So we did the study for Wilmington, North Carolina. I think that was one of the hotspots, and in Seattle, where they had many of these leaky condominium problems, they call them. And then we try to find what would happen if you do the same thing in Europe. Until that time, we didn't have a lot of externally insulated light bed structures in Europe, because the light bed structures in Germany are thicker. Walls usually are 36 centimeters thick or something like that with brick. So if you do a light bed structure, you might go down to 20 or something like that. But it's more than 2 by 4, so you have more than 4 inches. So you can put much more insulation in it. But now, since the energy requirements became more stringent, people are also trying to put on top of that the insulation layer on the outside, also in order to get rid of thermal bridge effects and things like that. So we will sooner or later have this, or we have this problem now also. And luckily, we had a company that learned all the problems and how to solve them in the United States, like Stoll. Sometimes it can happen. We'll see that later. Okay, so these are the boundary conditions driving rain loads in the different locations that we were looking at. And you see they're all pretty high, maybe not in Vienna, but all the others are pretty high. This is relative humidity and max and minimum temperatures in July and January. Well, not much difference. Lisbon is warmer. It's clearly warmer. And then we did simulations and dumped 1% of the rainwater behind that exterior insulation layer, where it would go if your window wall connection was leaky. And looked at the OSB, and we knew that anything above 20% biomass is a problem. So we had, first of all, a simulation where you had no leakage at all. You can always assume it. It's not real, but you can assume it. And you see, okay, then it works out. That works fine. At the interior side, we had a polyethylene film. That's something that they usually used as an air barrier and vapor barrier in the United States. As you need an air barrier everywhere. I don't know whether you need a vapor barrier in North Carolina. It doesn't get so cold, but it can be a good idea. So we tried with a different type of vapor barrier, one that we called smart vapor retarder, that changes its diffusion resistance with the relative humidity, much like Intello, but I think Intello is for your climate even better. And you see, okay, It doesn't work with the polyethylene, and in Wilmington, it would work probably with that smart radio vapor retarder. So adding a driving potential towards the interior can help even if you have rainwater leakage, because water can dry out in both directions. Towards the exterior, it's difficult here because that insulation layer has a vapor retarding effect. If you had mineral fiber insulation, which I said would be a better idea, and you can do the calculation and find out it's a much better idea. But this was unheard of. I think in the United States at that time, they didn't use mineral fiber or stone wool. It is stone wool boards as insulation. We do this in Germany more and more, but they are more expensive, of course. Then it's not a cheap system anymore. That's a problem, but has many other advantages. It's fire resistant and everything. So it's not bad, but it's expensive. So here we saw already difference. So you could at least alleviate the problem. But only if you had just 1% of rainwater. If it was too crappy, then it would fail. There was no doubt about it. Then we did the same calculations for Hanover and other locations, and we found, well, doesn't really work very well there. Why is that? Because the inboard vapor drive in Germany is much less than it is in North Carolina. Walls don't get that hot outside. So whether a drying potential really works or not, the question is also where are the highest temperatures, and in which direction. And here apparently it wasn't good enough. So you could say no solution there. And so we did simulations over 3-year periods and looked at the critical moisture content of the OSB for the different locations. And we saw, well, you can find a solution with that smart vapor retarder when the climate is warmer, like Lisbon, Locarno, or you have less rain, like in Vienna. That also works. But the best solution was always to have here mineral fiber insulation on the outside, so stone wool. Then you don't get a problem because now the water can dry out towards the exterior again very easily. And those who've been here before have seen in the morning that how a wall dries out depends on what the insulation layers are, whether it dries towards the exterior or not. Okay, so we carried on with that and did a study for a masonry or concrete wall, especially masonry wall. We saw, well, if 1% of water gets in there, it might be a problem or not. So what we did the simulations for Holzkirchen and Krakow. Krakow is in Poland. The difference is Holzkirchen, where I come from, has a higher driving rain load. Krakow has colder winter periods. So the question is, what is essential here? And you will see when we look at the results here. In Holzkirchen, it's getting wetter. You get more moisture in it. This is what I would have expected because of the higher wind-driven rain load. Differences are small when you have mineral fiber, mineral wool insulation. And again, if you compare the amount of moisture that you get into the masonry with the amount of moisture that will be in the masonry at 80% RH, so that's equilibrium moisture content. This is what we assume. Everything that's below that equilibrium moisture content of 80% is assumed to be dry. A building material is never really dry. It always has some moisture in it, but this is the threshold. So as long as you are below these 80%, this is also for energy calculations, when you determine the thermal conductivity, that you take that value at 80% RH most of the time, at least in Germany, but also in other European countries. And then you see, well, all these water constants that you get after 10 years, now you had to do a calculation over 10 years because it takes a while until masonry has picked up enough moisture that it's in a what we call dynamic equilibrium. Picks up some in wintertime or during the rainy season, then dries out again. So 10 years is a good time to do the simulation. You'll also see that the increase in moisture content will level up. And but you see we are always well below it. So 1% of water, if it gets behind at the window junction behind the insulation layer, it doesn't really hurt anybody. Now the question is, how much do we get? And during the time when we worked together with Americans, we also did advanced movie seminars for them and showed them our field test site. And they went around, looked at the window connects and said, well, this must be leaking. I said, what are you talking about? It doesn't leak, it works perfectly. I said, no, it's not well done, it must be leaking. So what did we do? We tested it. We had a building like that was around for 20 years with that external insulation layer. It doesn't look very pretty on the outside. It's because sometimes you get the growth of algae or fungi, but there was no problem, no damage. Then we took samples, and from the polystyrene, see, it looks good, no problem. And then we weighed them, put them on scales, dry them back on scales, and found out that we got up to 10% volume percent of moisture. That's quite a bit. That's 100 kilograms of moisture per cubic meter. We back calculated that and found out that there was much more than 1% of the wind-driven rainwater going behind that insulation layer. So, and therefore, with that knowledge, what before, when you say, well, it all works, and the company goes to the United States, does the same thing, but on a different construction, and then it fails. Now, we know where that comes from because it always failed. This was one of the houses, and I also tested another one. Where's that now? Okay, this is the right one. Below the window, can anybody guess what happened here? Sorry? Yeah. No. Well, ants and other insects like it when it's warm and humid. And they crawl behind it. Again, from the outside, you didn't see anything. Maybe if we had lived, these are test houses. If somebody had lived in the house, would maybe have discovered that there are many ants crawling around. I don't know. We didn't see anything, but they were behind it. So again, you see, this is not a very good thing. But nobody knew about it because usually you don't do tests like that. As long as there's no damage, there's no reason why you should cut that up and look what's behind it. It was just because the colleagues from the United States said, well, this must be leaking. And I said, well, if they're right, then I'm going to find out. And they were right. So this is, I think, quite important. And the difference is always, if you apply the same system to a different wall, it can behave completely different. With masonry, I think you can do almost anything with concrete. This is not moisture-sensitive material. But masonry is sensitive to earthquakes. So it's maybe not a good solution for New Zealand. You have to look for something else. And therefore, and this is what Stoh learned, and now they train everybody, because we also have now lightweight structures in Germany where we apply steel insulation systems, how you have to do the detailing. And this is the last slide. So what you've seen down here, detailing and flashing that we've never done, because we were not used to having drainage paints or anything like that. We were just used to having a face seal, and we believed it worked, but it does. You don't see immediate damage. And I must say, these 10% of water volume percent in the insulation layer are not very important if you reckon that it's just beneath the windows. All the rest is still intact. So, and with 10%, it still has a lot of insulating capacity. So it's not that the R value goes down dramatically. Okay, I think this is the point where I hand over to Jesse